Alright, hello everybody. So this one we're going to talk about splay trees. Splay trees are the second kind of self-balancing tree we're going to look at, and they're different from AVL trees in that these are amortized balanced. So they're never like perfectly balanced. In fact, they don't even have like a definition of what it means to be balanced. But every time we do anything to the tree, any time we sort of perform any binary search tree operation, we'll tweak the tree a little bit to make it more balanced on average over time there like that. The other property that splay trees have is they're adaptive, so they tend to keep the keys that you access like sort of frequently near the root where they're faster to access, and then keys that you don't use as often get pushed out to the fringes of the tree here. Like AVL trees, splay trees rely on rotations to kind of manipulate the structure of the tree while preserving the binary search order property. So we're going to keep the sort of basic, insert, remove, and find operations from binary search trees here, but what we're going to do is after every operation, and yes, that includes find, so even find we're going to do this here, right? We're going to perform a thing called a splay starting at the target node there. For find and insert, the target node is just like the node, right? So for find, n is the node that we found. If we don't find it, then we use the parent of its node. For insert, n is the new node that we added. For remove, of course, the target node gets removed, so we use the parent of the removed node as the sort of node that we're going to start the splay operation at there, like that. So insert, remove, find, those things don't change, but at the bottom of them, right, we're going to call this splay function here. So the core of splay is a loop that sort of runs from n up to the root of the tree here. Splay trees usually require our nodes to have parent pointers. You can kind of tweak it to like not require parent pointers, but it's a lot more fiddly to do it that way there. But we don't require any kind of height information, unlike AVL trees there. Splay is going to run in O of h in the worst time, and again, the whole point of this is to make it so that our height is sort of like the log of our number of nodes here, like that. So splay is going to run in log of n time there. Splay is going to perform specific rotations on n based on how n sort of relates to its parent and grandparent nodes there. And then since rotating n has the effect of kind of like moving it up, a side effect of splaying is that n is going to become the root of the tree there, like that. That's not the main purpose of a splay, but it is like a side effect. But we'll see later on there are situations where you want something to become the root, and then you can intentionally splay it, and then the balancing behavior is like the side effect. So here's a sort of sketch of the splay algorithm, and we'll go into it in more detail in a second here. So as long as n is not the root, we're going to run a loop that basically is like, while n is not the root, and then we're going to check n's relationship with its parent, and if it has one, its grandparent here. And then there are three cases that this can break down into. So case zig occurs if n is a direct child of the root, which means it doesn't have a grandparent, so we don't have any grandparent to look at there. If we're not in the zig case, then we have both a parent and a grandparent, so we can look at our relationships to both of those here. So that breaks down into two cases. A zig-zig is if n is a left-left or right-right grandchild, so we have like n and then its parent and then its grandparent, or going the other way, grandparent, parent, and n all down to the right like that. That's called a zig-zig. And then a zigzag, as the name suggests, right, is if it is a left-right or right-left. So that means we have like an n, a parent, but then the grandparent is over here, or going the other way, right, grandparent, parent, n down there like that. So this down here would be a zigzag. These up here would be a zig-zig there. Zig is the easiest case here. So again, remember, zig is if n is a child of the root here. All we have to do is rotate n with the root. So if we start out in this configuration here, where n is a child of the root, and then we rotate n with the root, then we're left with this configuration like that. And note that now n is the new root of the tree after that rotation here like that. Now, one thing I'll mention, right, is, of course, there's a mirror image of this one here that looks like root and then n down here on that side. I'm not going to draw all the sort of mirror versions of these cases here, so I'm only going to draw like sort of one half of the cases, and then it's just there's just the mirror image left, right mirrored of the other one there. So just to save some space, I'm only going to draw half of the stuff here. So zig is easy, just one rotation, and then we're sort of done there like that. Zig-zig is if n is a left child of its parent, and then p is a left child of its parent, which is the grandparent, or the other way, right. So this, again, this picture depicts the left-left situation, but there's a mirrored right-right situation here. So in this case, we're going to do 2 rotations, but this is not a double rotation. We are first going to rotate p with g, and then rotate n with p. So if we're over here and we rotate p up with g, that gives us this configuration here in the middle, like that right there. And then we're going to rotate n with p, which moves p up to the top here. So it basically goes from a shape that looks like that, with n being down onto the left, to a shape that looks like this, with g being down onto the right there like that. This may not look like any more balanced than what we sort of had before there, but we'll see later on that like the zig-zag case, kind of like why it kind of works like this here. So we do 2 rotations, and note that n moves up 2 levels in the tree. It sort of starts 2 levels down, and then it's moved 2 levels up when we're done with the zigzag there. A zigzag case is when n is a left child of p, and p is a right child of g, or vice versa here, right? So we have this kind of zigzag shape here. And if this looks like the inside imbalance from AVL trees, like, you're not wrong, and we're going to treat it the same. We're going to double rotate n. So first we're going to rotate n up there. That gives us this sort of shape here in the middle there like that. And then we're going to rotate n again, which gives us the final shape over here on the right-hand side there like that. So again, notice that n has moved up 2 levels in the tree, but in this case it's a little bit more obvious how the sort of rebalancing works, right? The tree is kind of flatter when we're done than what we started with there. All right, so here's an example of just running through inserting some stuff into a splay tree to kind of see how it works here. The first insert, of course, doesn't do anything because the thing is immediately the root, so 12 just becomes the root to start there. 78 is going to go to the root's right, so we start by just doing a normal insert and putting 78 where it ought to be. Then we do a splay, which means we ask what case is 78 in. It is a child of the root, so that is a zig. So we're going to rotate 78 upwards. So after we're done inserting 78, this is the sort of tree that we're left with there. Now 34 is going to be like sort of, again, we do a normal insert, so we say where does 34 go? It goes as the right child of 12. So we place 34 down there like that. Then we ask what situation is 34 in this tree, and this is a zig-zag like that. So we do the zigzag action, which is to double rotate 34, and that produces this tree over here, like that. So this is the final tree after inserting 34. Next, we're going to insert 96. Where's 96 going to go? It's going to go down here as 78's right child, like that. So again, we look at this tree, we do the normal insert first, and then we ask which of the 3 cases is this? This is a zig-zig. So we're asking, how does 96 relate to its parent? It's a right child. How does its parent relate to the grandparent? It's another right child. Right, that's a zig-zig. So what do we do for a zig-zig? First, we're going to rotate the parent. So the parent is 78. The grandparent is 34. We're going to rotate 78 up first, and then we're going to rotate 96. So if we do those things here, I'm sort of skipping the intermediate step here. That results in this tree here, which again does not look very balanced here, but the sort of balancing effect of splay trees is not at any particular instant. It's an average. It's amortized over time there. 96 is the root, so we're done with that one. Then we're going to do 61. Now, where's 61 going to go? It's going to go right here. So there's where 61 starts, like that, right? So again, we look at how does 61, which is our node, relate to its parent and its grandparent, and it is a zigzag case here. So we're going to double rotate 61, which results in this tree over here. Now here's the thing. we're not done with 61 yet. Remember, the loop runs as long as the node is not the root, and 61 is not the root yet here. So I'm not just going to do one sort of manipulation here. I'm going to ask, what case is this? And this is going to be a zig case here. So going over here, again, looking at this, that is a zig case. What do we do for a zig? We rotate 61 up with 96. So this is the final tree after inserting 61 there. We had to do sort of two cases to get it there. Finally, where's 52 going to go? 52 is going to go here, right? So we put 52 there. We ask, how does 52 relate to its parent and its grandparent? It's a zigzag case. So what do we do for a zigzag? We're going to double rotate 52, which gives us this final tree right there. That's the tree that we end up with after inserting all those values into it there. Now, usually we'll use Splay inside of, insert, find, and remove, but you can use it in a few other situations. Like any situation where you want to take some particular node and move it to the root, you can do a Splay. So an alternate implementation of remove would work like this. So first we're going to find the node that we want to remove there. Now, if we're using the sort of Splay tree find, this will have the effect of splaying that node to the root of the tree there. So the X node is now at the root of the tree. That means our tree has like the node we want to remove there, and then some subtree over here, and then some other subtree over here. And of course, everything over here is less than X, and everything over here is greater than X there. Then we just delete the root, right? So it's just gone. That guy's gone there like that. And that leaves me with two detached subtrees. I have a left subtree and a right subtree, and I know that everything in my left subtree is less than everything in my right subtree. So then I'm going to take my left subtree and I'm going to find the largest element in it, so something like down here, right, and splay it to the root. So what that gives me on the left-hand side here is a new subtree that has some node at the top, and then the rest of the tree is down here to the left of it. There's nothing over here on its right there, because we grabbed the biggest element in TL and we splayed it to the root here. So like it has nothing on its right because there's nothing in TL that's greater than it there, like that. And then all we do is we just take TR, this tree over here, and stick it on under there as the right-hand side. So now I have a new tree that doesn't have X inside of it here, and it runs in O of H time, where H is going to be the log of the number of nodes if we're using Splay trees for everything else there. So it's a little bit more straightforward way of removing things than the kind of like, messy three-case version that we learned about earlier there. There's a few other things that you can use Splay for that are kind of similar to that there. Now, the sort of full analysis of Splay trees requires like sort of more fancy amortized analysis methods that we haven't covered. Like you have to learn about like the potential method and stuff like that. But you can get kind of an intuition for why it works here. So the zig case, we only ever do that once, right? Like, at most once. Sometimes we don't do it at all there. So it doesn't have a big effect on like the rebalancing of the tree there. If the tree was balanced before we did a zig, it'll still be balanced after we do a zig there like that. If we do a zig-zig, the idea behind it is if we found N like sort of down here on the left, right, like that, that sort of serves as a little hint that maybe there's just too much stuff on the left-hand side of our tree, and so we should move some of it over onto the right-hand side. Or vice versa, maybe there's too much stuff on the right-hand side and we should move it over to the left there. If we have a zigzag, right, where we have grandparent, parent, and N, like, again, this sort of shape of the tree here serves as like a little hint that maybe there's too much stuff on like the interior of the tree and we should try to move it out to the edges, which is exactly what that kind of double rotation tends to do there like that. So we kind of like the different cases are kind of like, the tree kind of looks like this, so maybe we'll do a manipulation that will sort of fix that kind of thing. It might not be the right manipulation every single time, but on average over time it all tends to sort of work out there. So anyway, to sum it all up, our Splay trees are amortized balanced. If you just look at them at like a sort of a snapshot, you'll be like, that tree's not balanced. But if you do it on over time, sort of look at it on an average here, it sort of tends to balances out there like that. And the key is this splay operation that moves into the root while rebalancing the path from end to the root. All right, that'll do it, everybody. If you want to look at the video about assignment 4, you can do that now.